Hey guys, can I get a sound check?
I can hear you.
Great, thanks. Zoom myself in. All right. Hmm. Hmm. Arthur, you're already falling asleep. What is that emoji? Is that a sleepy emoji?
Pensive.
It is?
It's pensive emoji.
Pensive. Wow, that's a complex emotion, man. Hmm. Hmm. I keep trying to like remember what it was like to be in my sophomore year in undergrad. And I just have like really horrible memories. I can't remember any good things about it.
Probably because it wasn't really good.
What's
And you
that?
just probably it was so bad you just want to forget about it.
It was pretty awful. It was pretty awful. Yeah. I think my junior year it was definitely better, although it was pretty that was just a lot of work, but at least I didn't was more cheerful. And then senior year I was just I don't know, it's a blur. And then graduate
Is
school.
that for your college years or for your high school years?
Oh, that was for my college years. High school years were I was having a lot of fun my high school until we moved my senior year in high school, and that was kind of cramped my style that last year. But yeah, no, this is college. College was sophomore year was bad, very bad. So anyway, I don't envy you guys. Life's
Well,
better
I don't
than.
like my.
What's that?
Well, I don't really like my sophomore years right now because of this.
Yeah. You know, the first time I ran into somebody who said they liked school was about 10 years ago. It was, no, 14 years ago. It was one of the guys we hired from Cal Poly into our company. And we were talking about, you know, we're just sort of, I was just going on and on about how what a nightmare school was. And then he said, "Oh, I actually like school." And I was like, "What?" He's like, "Yeah, I like school." And I was like, "Man, you're the first person who's ever told me that." I mean, I'd had friends that had told me they liked school, but then they weren't really in engineering school. So that kind of made more sense. But he also happened to be, this guy was a valedictorian of the class he was in. So that might explain something. That's why I made him cheery. Okay. Okay, guys. So enough trash talk about school. Let's actually do some schooling here. So we sort of, I hope I put to bed the sort of like the diode equation, but I'm gonna say it one more time just because I just like trying to drill this in your head. The important thing that I want you guys to get out from what we've been doing is we're trying to create a simplified model of the diode. In fact, two simplified models of the diode to allow us to do hand calculations. And really that's it. So, I mean, it's like, there's a lot of, might seem sort of complicated, et cetera, but really we're just trying to do two models of, we're saying the base diode model is this thing where, current versus voltage. And then we have I sub D is I sub S, exponential of VD over V sub T minus 1. Do not forget this equation, very important equation. And, this just goes into ID, just becomes minus I sub S when VD is less than 0, just the math. And then it becomes I sub S exponential of VD over VT when VD over VT becomes much larger than 1. And remember that VT is about approximately 26 millivolts at room temperature. And if you at room RT, and if you need to calculate it at other temperature, it's just KT over Q. But all these are K and Q are physical constants, and T is a temperature. Okay. Let's see. I think the important thing I'd like to mention here is that let's draw this curve as an exponential, but remember this curve is extremely steep, very steep. It means that if the voltage change when you're in this sort of along this curve, when you're sort of really taken off here. So this would be somewhere around 6 to 800 millivolts. Okay, if your voltage changes by 60 millivolts, current I sub D changes by 10x, which is a huge change. Okay, that means if you have a diode and you try to forward bias it by a volt, you'll never be able to get a volt across it unless you've got, thousands of amps. Your diode's gonna like blow up way before then, right? It's just as if you have really a straight line, very close to a straight line. And if you simulate this in SPICE, you'll see that it gets, it's a very, very sharp interaction. Are you guys having a lag problem with the video?
I guess it's a little bit better now, but just earlier it was like lagging pretty hard.
Yeah. If there's any problem, it's probably on my side because I live in the boondocks with really bad internet. Okay. So anyway, these are like, I'm trying to think of all the key stuff to think about here. Okay. So those are the key things. And then again, what we're doing with the two other models is we're just trying to create some simpler model of this, so it makes life a little easier for circuit analysis. And so we have two models. One is what's so-called ideal model, which is VD I sub D, which again, like I was saying, this thing really takes off very fast. It's like a sharp, very sharp and hard to draw it. And I'm drawing it like an exponential. It is an exponential, but if you zoom out a little bit, it's just going to look like a sharp line. And that's what we're trying to emulate here. And then there's the model of V sub D. Where's this I sub D? This is the constant voltage model. And it's like this. Okay, this is VD on. Okay, so so what's the difference between these, practically speaking? Well, if you thought of yourself as like a human computer, okay, if you tried to use this model in your circuit analysis, you would start, you would plug in the model and you would start iterating a bunch of essentially differential equations, or you just start iterating a bunch of numeric equations till you got to the answer. And we've done that in the homework and a bunch of tries. So that's kind of this model. Basically plug it in, you start making an assumption. So kind of SPICE, the simulation tool, does that when you do it, when you simulate circuits. It really does this. So it actually assumes an initial condition. It calculates the voltages and the currents in and out of all the nodes in your circuit. And then it's just a bunch of differential. It's just iterating. It's just iterating to get all of these nodes to converge. And it's just like a computer, and it is a computer. It's just, that's all it's doing. Okay. What you're doing in these two cases is like you're a human if-then statement. And by that is, like if VD is greater than 0, you use, one model for your diode, which is a closed switch. So if VD is larger than 0, VD becomes this. If VD is less than 0, it becomes, your diode becomes this. So I don't like, anyway, I'm just trying to give you guys an analogy. So like you're kind of running two branches of the program and looking at both cases, and then you have to look at the special case where they come together. I don't know if that helps or confuses you, but that's how I look at it. And then this is very similar. The constant voltage model is, again, two if-then statements. If VD is now less than VD on, the diode is an open circuit with some VD on. And if VD is larger than VD on, get a closed circuit. And just keep an eye out on making the right polarity here. I hope I did there, but anyway, that's the thing to worry about. So this is like the sum total of everything we've been doing. And as far as the class is concerned, as far as your homeworks and quizzes and all that good stuff, you just got to try to do like a bunch of homework problems to get used to using these analysis techniques for various small circuits, which is what we're dealing with. So that's where things are at. Okay. So any questions about any of those? Okay. So these are simplifying models of the diode, and this type of behavior of a circuit element, this type, when you're looking at things from like minus infinity to plus infinity, is called the large signal model. Large signal model means that, so this is another, now we're transitioning to another simplifying model. Okay, so the non-simplified model is the large signal model, which is from minus infinity to plus infinity. This is what the device does. Okay, for a lot of circuit problems, what happens is you're not really concerned about what happens from minus infinity to plus infinity. You're really just concerned over a little bitty area. That's all you're concerned about. You're like, let's say in the case of like a microphone, going to an amplifier. A microphone, like the voltage coming out of a microphone, I'm not an audio engineer, but is probably in the millivolts. It's not from minus infinity to infinity. It's like a very tiny voltages coming out of a microphone. And you're trying to amplify that to, maybe a few hundred millivolts or something like that. So you're really like, if you just look at where a lot of applications are, they end up somewhere, if you were using a diode, just a small part of this IV curve here. Okay. So for a lot of applications, using the large signal model is kind of an overkill. So what people have done is created something called, and I'm gonna go into this in detail, but I'm just trying to give you guys the sort of the big picture. So again, this is VD, this is I sub D, and so the curve is like this, and the equation is and over here, the equation is ID is I sub S exponential of VD over VT, approximately. Okay, so here we still have this kind of equation. So this would be called the large signal model. Large signal, this is large signal. So what does a small signal look like? Well, what we'll see is if you have an application like that, like I talked about, like the microphone, and a lot of applications are like that. Like when you're talking about a receiver on your cell phone. Now imagine the receiver on your cell phone is like a small antenna. You guys probably haven't had any RF or radio frequency or radio classes, but it's a fairly small crummy antenna around your cell phone. And you have a cell phone tower somewhere, I don't know, like many meters, yards from you. Okay. So by the time that signal arrives at your cell phone and gets converted to a voltage, we're talking about a really small signal, again, hundreds of microvolts to millivolts. You're not going from minus 10 volts to plus 10 volts on your cell phone receiver. Okay. So and anyway, I can just go on and on where it's just the nature of the nature of our nature, the nature of auto interactions with the environment is whenever you're sensing the signal, let's say you're, somebody's using a, I don't know, what's it called? Shoot, I'm forgetting the name, but let's say they're doing some medical imaging on you. Okay. So they're, taking an x-ray, something like that. The signals you receive at your detector are always like very small. Okay. It just happens over and over again. Okay. So what does that mean? So that means that you can, and it's a very powerful thing to do, create what's called a small signal model. And again, like I said, all we were doing in the previous lectures is trying to create these simple to use models. So here's another model, which is trying to be a simple to use model. And it is. Initially, it's going to look confusing. But what does the small signal model means? It means that if I zoom in all the way down into so this is my exponential curve, I'm going to zoom the heck into here. Okay, I'm going to just zoom way in and just look at, I'm saying I'm just going to use this part of the curve. Okay. And the idea here is if I just look at a tiny part of the curve, this is just going to look like a line. Okay, I drew this badly. So if I just, whoops. So I'm going to just use another color because otherwise I'm going to get. So again, I'm zoomed in to this part of the curve. Let's say here, this I can model as if it was a resistor. Okay, so instead of saying just for this tiny part of the curve, I can say that ID is sort of V sub D times like some, I can think of it as a equivalent resistance. Okay, just for this teeny part of the curve. Okay, so again, I'm like, if I zoom out, this simplifying assumption is only true for this part, for this tiny bit of the curve, as long as I know for a fact that I'm only operating there. Okay, and if I have another device that's, let's say, operating here, it'll have an ID that would be V sub D times another equivalent resistance. So, because the slope of this side is different than the slope of this chunk. So it's as if I have, so I would have to figure out where I am here. But then once I know I'm just here, I can use like a simpler model than an exponential model. And we're going to get into that. Does that, yes, go ahead.
So for this one, it's I equals V times R, not V divided by R.
Oh, I'm sorry. It's V divided by R. Sorry. Thanks for pointing that out. Got ahead of myself. This is V to be divided by R. Thanks, Darren. Hopefully I didn't. Any besides that? Besides having a foolish professor, any other questions? No. Okay, we're gonna get into it, but that's a sum total of what we're trying to do. We're trying to create a model that you can use a lot, surprisingly large. Most of my circuit design activities happened, right here. And then sometimes you have to pop out and make sure it works, over what the customer is specifying. But it's a very, very powerful modeling approach. Okay, so the first thing we're gonna do before we go into that, we're gonna, I don't know if I should do this, but yeah, well, anyway, it's a little confusing, but let's just do this as the first thing, which is an example that the book has about what you would have to do if you did not have a small signal model. What would you have to do if you were forced to use the large signal model? Okay, so we're going to look at this first and see that, it's somewhat painful, and then start our study of the small signal model. Okay, so this is the conceit of the problem. Okay, is that the idea is you've lost your cell phone charger, and your cell phone takes you're trying to build your own cell phone charger is the problem. Okay, so what you'd like is, at your cell phone wants 2.4 volts DC. Okay, you went to the store and found some kind of an adapter that plugs into the wall, okay, that outputs 3-volt DC. And the question is, well, what could you do to go from 3 volts to 2.4 volts so you could use this as your cell phone charger? So the problem suggests that, well, we know that typical VD-ons for diodes are, let's say 600 to 800, 900 millivolts, something like that. So it seems like if you put 3 diodes in series, and they're all forward biased, notice this, for all of them, this side is 2.4 volts. So you start with that assumption, and this side is ground. So they're all forward biased. You could get them in a situation with each one has 800 millivolts of 800 millivolts of V sub D. Okay. So 800 millivolts times 3 is 2.4 volts. So seems like, if you put 3 of them in series and used a resistor to sponge up the rest of the voltage, then you could create a 2.4 volt voltage thing here. And so what the problem is saying is, let's say you go to the store and they're selling some different diodes, and you want to pick one for these 3, or pick 3. And the question is which IS to pick. Okay, so basically if this is at 2.4 volts, okay, you have a certain current going through this resistor. So this current through this resistor is I sub X is let me just write the whole thing. Ix is 3 volts minus 2.4 volts divided by 100 ohms is 6 milliamps. Okay, assuming you could get to 2.4 volts. So the question is, okay, I have 6 milliamps going through these diodes. What I sub S do I need to get 800 millivolts? Okay, so this is a problem. Like when you go and buy a diode or get a diode in the lab, you'll get a spec sheet, and one of the major things in the spec sheet is the I sub S. Okay, and it kind of tells you pump so much current into this, you'll get so much voltage across it. So okay, well, we have an equation that says for V sub D as a function of I sub S, and as V sub D natural log of Ix over I sub S. Okay, or we have I sub x is I sub s exponential of Vd over Vt. So those are our two equations. Okay. In this case, we know we want Vd to be 800 millivolts. We know we have an Ix of 6 milliamps, and Vt is, a constant 26 millivolts. Okay, so we can just calculate I sub s is 6 milliamps over exponential of 800 millivolts over 26 millivolts. And I think I get, I get some number 2.6 times 10 to the minus 16 amps. Okay, so that's our initial answer. Okay, not too bad. Okay, so if we can buy a diode with roughly that I sub s, and we pick this resistor value, we can get 2.4 volts here. Okay, now the second part of the problem though shows you like the kind of the difficulty here is that it's Melvin, did you have a question?
I didn't know it was unmuted.
Oh, no. Okay, just clearing your throat. All right. So, all right. So this happens all the time in that sometimes you don't get 3 volts or something changes. Okay, and like here, 3 volts might easily change to 3.1 volts. Okay, well, like, okay, so now you're in a situation where you just did this calculation. Now you got to see what happens if this is not 3 volts, it's 3.1 volts. So you go, okay, geez, what do I do? Well, let's say my 3.1 volt, I'm going to start assuming a bunch of stuff. Assume most of the delta V, which is 100 millivolts, drops across the resistor. Okay, why can't I do that? Because the diode, it's got a very sharp, transition here. That means if the current changes by, we said if a current changes by 10x, V sub D changes by 60 millivolts. Okay, so here in this case, the current went potentially from 6 milliamp to 7 milliamp. So the current changed by, like, I don't know, maybe by what, 15%, something like that. I'm just sort of really, so delta V is going to be, much less than 60 millivolts, right? It's going to be in the single digit millivolts probably. So the delta V's aren't going to change very much. So we can say that most of this voltage drops across the resistor, which means that basically I sub s changes to, 7 milliamps over exponential of 800 millivolts over 26 millivolts. Okay, and then we can basically calculate this. We can see what that delta V does to this thing. But basically, we're like going to get into the iterative procedure and like seeing what the different options are. So it seems like if we had like a small signal model where we could just come up with an equivalent resistance here for these guys, like we talked about here. So if we had, these guys are right around 800 millivolts each, right? That means we kind of know that they are somewhere, if this was 800 millivolts, we'd know they're sitting kind of right here. Okay, so if we'd come up with an equivalent resistance for them, for the diodes here, this would look like something like this. It would look like a resistor, a 100 ohm resistor, and then, whoops, let me find someplace. So it would look like a problem like that. It would be like a resistive divider problem. So, you know, we could see if you have a delta V here, it would just be a ratio of resistor type of calculation to figure out what the change in voltage is here. So that's kind of, this is the type of problem that's a motivation for the small signal model. Okay. All right. So okay, so let's get into the details of the small signal model. And the idea is once you're in forward bias, okay, so let's say you're going, you just know for a fact, so this is V sub D, this is I sub D, so we're in this forward bias part of the equation where here the large signal model says it's this exponential equation. Okay, now let's say that we know for a fact that we're only going to be going between these 2 points. So we're going to go from VD1 to VD2 only. And I sub D is going to just go between these 2 points. So in the case of our earlier problem, so each VD1 was, you know, the VD1 started at 800 millivolts and maybe they went to, you know, I don't know, 805 millivolts or something. Okay, for each VD1. So we know we're only operating between these 2 nodes. And if you know that, what you can do is just assume that the change in current is just the change in voltage as a function of this ratio. Okay, because okay, so why I sub D1? Okay, because we basically what we want to do is well, let me just actually show it to you guys. I guess this is this is sort of the proof of why this ID1 over VT, why this happens. Okay, so we start by looking at the exponential equation. So ID is I sub S exponential of VD over VT. Okay, and then we take the derivative of ID with respect to VD. Okay, and then we end up with IS exponential of VD over VT over VT. This is taken at VD is equal to VD1. Okay, so VD1. So this is equal to, so notice that this term is the same as ID. Okay, so this guy is just equal to I sub D. Okay, so this derivative of ID over VD is just I sub D over, that's really ID1 because it's VD1. ID1 over VT. Okay, I'm just actually just rewriting this, I guess, or showing you guys how that works. So the reason why it works out like this is just because you have an exponential equation. And if you take the derivative of the exponential, you basically get the exponential itself with just, you know, the constant and the derivative coming out. Okay, so what does this tell us? So, well, v sub t is a constant, right? It's 26 millivolts. Okay, so basically what this says is it's as if I have a resistor. So if I want to get a delta I sub d, so I mean, I do this again, v is equal to IR, so I is equal to v over R, so is delta v sub d ID1 over VT. So it looks like I have a resistor of value VT over ID1. And so this is our equivalent resistance. Any questions about what I just did? So let me walk you guys through the top high levels of what we tried to do. So we said we're only gonna zoom into a small portion of this and guarantee that we're only gonna stay in the small portion. Okay. And then what we did was we said, okay, well, if we're in that small portion, let's, we keep what we assume our center point constant, that's VD1. And if we try to find the slope right here, just that there's one, we can pretend this is almost 1 point, these things being very close to each other. So we can take the derivative of that point, and that derivative, because the curve is exponential, is gonna look like a resistor with a resistance that's inversely proportional to the bias current. Okay, that means that as I move up this curve, okay, the slope, as you move up this curve, the slopes, so as you go from here to here to here, the slopes are going to get, sharper and sharper, meaning that this resistance 3 is less than resistance of 2. This is resistance of 2 is less than resistance of 1. This is resistance of 1, meaning that as you increase your current, I sub d, or increase your VD, this equivalent resistance goes lower and lower and lower. Okay, but in all cases, this small signal resistance is this equation, which we just sort of calculated here. So this equivalent R sub D, if you say I'm only operating a small area, you can make our circuit here, which is, voltage source, a resistor, and a diode, look like basically a resistive divider equation, with this resistance being V sub T over I sub D. Any questions, guys? No? Okay. So let's sort of look at an example here, right? Let's say we have let's say we have a small voltage going into our diode. Okay, as a function of time. Let me just redraw this. Maybe it's better if we do this. So let's say this is our, whoops. Let's say this is our circuit. And this is a voltage as a function of time. And this voltage as a function of time as a sinusoid. Okay. So this is V sub 0. This is time. This is voltage. We got a sinusoid going in here. Okay, so sinusoid, if there's some offset, plus there like as a peak value. Okay, so that's a description for our input voltage. Okay, so the question is, what is our current? Okay, in this case. So if we tried to use the large signal model, we said, so this is, let's say V sub 0 is, puts us in a forward bias. Okay, so if we just use the large signal model, we would I sub t would be I sub s exponential of V sub 0 plus Vp cos of omega t over V sub t. Okay, so in this case, we have to take, whoops. In this case, we have to take an exponential to the power of a cosine with an offset added. Okay, so I don't know if by you guys, but this seems kind of daunting to me. Okay, to try to calculate this out. Okay, if we just look at the large signal model, or what we could just do is realize that we can do the small signal model. Why can we use the small signal model? Well, this is the input. So you see, if I draw sort of this voltage here with like sort of, if I superimpose time here and draw strata voltage, so kind of like that. The absolute value of the voltage is just going sort of a V sub p value around V sub 0. And if this V sub p is a small number compared to V sub 0, then I can just use the small signal model and say, okay, well, if V sub t is this equation, then I sub t is just it's is exponential of v0 over vt, okay, plus v sub p cos of omega t so that's our delta V, right? This is equivalent to and times I let me expand this out. times I sub s exponential v0 over vt over v sub t. I got that right? No, I screwed that up. Sorry, guys. It's v sub t over, I'm doing the v over r. So r sub d is v sub t over I sub d. So v over r, no, v sub t. What am I doing wrong here? V sub 0, v sub t over I sub 0. I sub t is v over r, and r is 1 over I sub d over v sub t. This equation right? Anybody see what I'm doing wrong here? V over R, right? V over R over. Yep, I'm thinking, I'm going to say I think this equation is wrong here. I think it should be I sub 0 over V sub t, V sub p cos of omega t, and not this. Everybody see what I'm doing here when I'm using the small signal model? You guys with me? No? Any questions? Arthur, supposedly that V over R is I. Yep. Are you guys
Wait,
hanging?
hold up.
Did I get this wrong? Sorry. Arthur, are you getting confused? As confused as I am?
Where's the large signal model equation you get from? Like IP of t equals I sub 0 plus I sub p times cosine of wt. Oh, is that from
So
there?
the large signal model is I sub d is I sub s exponential of v. So sorry. The large signal model is this v of t over vt. Okay, this covers everything. So the small signal model is I sub t is sort of this delta v I sub d over v sub t. It's like an equivalent resistance. So when I'm doing the small signal model, notice that this part is the large, sort of the large signal behavior, v sub 0. And this V sub P cos of omega T is a small variation. So this is a small variation over this V sub 0, which is the large signal. Okay, so what I do is first I can just look at this as two components. One of them is the large signal component. So I calculate what my current is at V sub 0. And then I have a small permutation around that current, which is just that this delta V over my equivalent resistance. Okay, and my equivalent resistance is V sub T over I sub D at, so I sub D is defined at V sub 0. Was that your question, Arthur? I'm just sort of confusing you more. See if there's any other examples here. Nah. Do you guys see what I'm doing? No?
Okay, I think I can understand why you get IS times EXP or something like that. But I'm sorry if you answered this before, but oh, sorry, I forgot my question. I'm sorry.
Okay, no problem, Arthur. Yeah, I think this, I'm pretty sure this equation is wrong, okay? So I think this is the answer, but the idea is that if you use this small signal model, you can basically, instead of trying to calculate some kind of an equation like this, which would be, whoops, where is this? Would be this, this exponential of a cosine. Okay, so this is like a pretty complex equation. You could just break it down into your current being a response to a large signal value, which is this V sub 0, plus a small signal response, which is just true right around this value, right around your large signal value. Okay, so this I sub S, okay, let me say this. So it's as if you had a resistor. So it's as if you had just a small signal part. Looks like you had, instead of this, it looks like you had a V sub T just the small perturbation. Okay, notice we got the small perturbation doesn't include this large value. So we're just taking the delta V, okay, across an equivalent resistance. So instead of a diode, it looks like we're putting it in across an equivalent resistance. And this equivalent resistance is V sub T, which is 26 millivolts over I sub D 0, and this I sub D 0 is defined as the value of I sub D here. So that's equal to I sub S exponential of 0 over VT. So it's as if I take this voltage and put it across this resistor. So just my small signal, I sub T, just my small signal is going to look like this VP cos of omega T over this R equivalent. So VP cos of omega t over V sub t over I sub s exponential of V0 over Vt. So is I sub s exponential of V0 over Vt, Vp cos omega t over Vt. Okay, and this part is just equal to I sub 0. Okay, so I can just write it I sub 0 over Vt, Vp cos of omega t. This seems to me like this is written like it should be I sub 0 over V sub t as opposed to V sub t over I sub 0. So again, let me just say it sort of another way to look at this is when you have a situation like this with a small perturbation around a voltage, okay, you can basically analyze it as if there were two components to this current. So if you draw this, I think if we just change this to time and draw the voltage here. So I took this, sort of rotated it, drew it here. It looks like the current is just going around between these 2 points sinusoidally. Okay, so it looks like there is a current that's just sort of corresponds to the center voltage, which is V sub 0. So there's a corresponding current called I sub 0. And then there's a sinusoidal current around that I sub 0. Okay, and the value of that sinusoidal current is just this voltage divided by the equivalent resistance that you get here from our linearizing model. Is everybody completely confused? Anybody not confused?
I was at first, but then
am
I saw
lost.
you do the formula again, and I kind of got it.
Sorry?
No, I said I was confused in the beginning when you first introduced the formula, but now you did it again right now, and I'm starting to get it.
Okay. So it's just we're trying to, like, believe it or not, is trying to simplify things and just trying to model a small change as a resistor when a diode is concerned. Let's see. So let me go back to this example that we had up front. Okay, remember we said we had these diodes, okay, and the voltage changed by a small voltage, some delta V here, okay, and we wanted to see what the change was in the voltage here. So let me redraw it here, what we started with. Okay, so the starting point was we had a 3-volt adapter that went from 3 volt to 3.1 volt. Okay, so this means that the delta V is 100 millivolts. Okay, and then we had a resistor R1, which was 100 ohms. And then we had 3 diodes. Okay, so what we can do here, what we're saying what we can do is we know that this was initially centered around 2.4 volts because initially we calculated these each as having a V sub D of 800 millivolts. Okay, so we know this is centered around 200 millivolts. So each one of these is centered around 800 millivolts. Okay, so we know that's the case, and we know that we just have a small delta V here of 100 millivolts. So now we want to see what happens. Okay, so what we're saying is we can assume that these diodes actually look like resistors, and these resistors, R sub zeros, are V sub t over that current that was flowing through here, I sub x. Okay, and remember that I sub x was, 6 milliamps. So R0 is equal to V sub t over 6 milliamps, or 26 millivolts over 6 milliamps, which ends up being, pull up my calculator for that one. So approximately 4.3 ohms. Okay, so just for the 100 millivolt part of this change, just for that 100 millivolt part, you can assume that this is the case. Okay, and then you can just calculate this as if you had a voltage divider. So these three R0s, this equivalent resistance is 3R0, or 13 ohms roughly. Okay, and this was 100 ohms. Okay, so V out, so this delta V out is 13 ohms over 100 ohm plus 13 ohms times the 100 millivolts. Or 11.5 millivolts. Okay, so meaning that, we didn't have to use an exponential equations to see what a small change would do to our voltage and current here. We could just use this really simple resistive model. Okay, and the model for the resistance is you have to get the bias point and then get the resistance for that. Okay, let me just, I know this is confusing as hell, so let me just say it from the beginning, so clear your minds. Okay, clear your minds. And I'm going to say it, I'll try to say it another way, but it's a difficult concept to get. So, whoops. Okay, so let's say we have our large signal model here. And so this is I sub d, and this is V sub d. Okay, and let's say we know for sure that we're only like operating around this small area. So we know for sure that V0, sorry, that our V input is only wiggling around this input. So from a V1 to a V2 centered around V0. Okay, which is a small range. What's a small range? Well, you got to say that this delta V has to be smaller than 26 millivolts. We'll see that later, but basically a very small range. So this thing is like 10 millivolts or 5 millivolts or something like that, this variation. And if that is the case, here we can just zoom in to this area and pretend that this is like a resistor just around this area. This is a resistor of value V sub t, which is 26 millivolts, over our center I sub 0. So what happens if you change this region to out here, So assume like you were out here. This R sub D is V sub T, and let's call this I sub, I don't know, I sub 1. Okay, so this R sub D is V sub T over I sub 1. And I sub 1 is much bigger than I sub 0. So R sub D2 is much, much smaller than RD1. So this, the value of this resistor, as you so-called bias this value. So if you add, if this was your V0, your resistance would be, equivalent resistance would be higher than if your V0 was out here. Okay, so by changing your center point, you can basically get this diode to look like different resistor values. So let's say you wanted this change here to be very small compared to 100 ohms. That means you would put more current through here. That way you would be operating the device. If you operate the device with more current, you would be centering it out here instead of here, and you'd have a lower equivalent resistance, and you would get a smaller change out here than if you were operating down here. Okay, so basically you're treating a diode in a very small range. You're treating a diode as a resistor whose value of the resistance is dependent on the center point where that diode is being operated at the voltage or the current at which you're moving, around which you're moving. Okay, so it could be a small value of resistor or a large value of resistor, depending on where you choose to center it. I don't know if that was any more useful or not, but anyway, that's the concept of small signal. And we're going to come to it again and again. And I think you're going to see a lot of homework problems. Yeah, so Arthur, yeah, the diode can be used as a resistor at certain points, at least from an analysis standpoint. Okay, the idea is a lot of problems are just like this, are just, your microphone is outputting 10 millivolts, sort of centered around 500 millivolts, and you can just pretend like, it's driving. If it's driving a diode, you can just pretend like that diode is a resistor for just those 10 millivolts. And this will be a lot more useful once we go into transistor behavior in chapter 4, but we're introducing it here. Anyway, my suggestion is do, again, like broken record, do a bunch of homework for problems with small signal, so you sort of get familiar with the concept. But we'll keep hitting this concept of small signal again and again, and it'll be much more powerful when we get to transistors. Okay.
To change the value of ID, would you usually change the input voltage or change the resistor?
You would change the input voltage, typically, for a diode.
Okay.
So essentially, you'd pump more base, you pump more current into the diode initially, and to reduce the resistance. Or if you want a higher resistance, you would just like run less current through it. Or, and less voltage. Okay, guys, so I'm going to leave it at that. Boy, I don't. Well, let's end here, because I think you guys are going to get saturated. We get into this part, which is now we're going to look at. So we came up with a bunch of models for the diode. Remember, we had these these models. So now we know these are models of different types of large signal behavior to figure out what your circuit's doing from a big picture. And then we have this small signal model to tell you what your circuit's doing with just small perturbations around a certain area. And the reason why this small signal model is useful is because in a lot of applications, a lot of applications, like 99% of applications, you're just dealing with small perturbations around some kind of offset. Okay, I can, as long as I can sit here and think of it, like if you have analog problem after analog problem, cell phones, microphones, you name it, driving a speaker, driving your display, taking a video of me giving this lecture over and over again. In the electronics, it translates into a very small perturbation in voltage or current around an offset. And that's what makes the small signal model or approach to solving a problem very, very powerful. Because again, it's changing stuff from exponential equations, natural log equations, etc., into just resistors, right? So just into linear equations. So that's the consistency that's in all these models. All these models are trying to take a device that's pretty complicated in its behavior. It's got this exponential characteristics, and trying to model it as a linear device, but under some very special circumstances. And you'll see this again in the transistor section as we go into next chapter. The transistor is much more complicated in behavior than a diode. It has 3 terminals instead of 2 terminals. So now you have 3 voltages that you got to worry about, and 3 currents as opposed to 2 voltages and 2 currents like in a diode. So now you're getting like more complicated. And so, the small signal model really, really helps you in analyzing those circuits. So I'm going to leave it at that, guys. And then we're going to come back on Thursday and start talking about the rectifier, which is probably one of, key applications of the diode when used as, an individual circuit element. So any questions? If not, have a good couple of, a lot to unpack. So have a good couple of days, and I'll talk to you guys on Thursday. Thanks, guys.
Professor,
Yeah.
is this going to be included in the quiz?
Yeah.
Well,
So the small,
what we covered today?
Yeah, what we covered today. Yeah. Okay. Well, that's a good question, Louis. So we said the quiz is what, next Tuesday?
Yes.
So yeah. So let's say we cover today and not the rectifiers. Okay. So you guys will. So we'll cover today and everything that came before.
All right. Thank you.
Okay, guys. Take care.
Thank you, Professor.
Thanks.
Thank you, Professor.
Thank you. Bye.